Dear students, let us discuss now the deletion operation in an AVL tree. Note down, this is an AVL tree that we have constructed out of these n keys. Okay, this is an AVL tree. Now let us consider the same AVL tree in order to find or in order to apply the operation of deletion. You recall deletion operation in the BST. The deletion operation in BST, there are cases, case 1, 2, 3. Case 1 says that deleting a leaf node, and case 2 says that deleting a node which has one child. Case 3, deleting a child which has two children. Okay, so you recall all the cases that we have discussed in the binary search tree. Exactly, we have to follow the same rule. When you are trying to delete a node, you check whether it is a leaf node or child which has one child, or a node which has one child, node which has a two child. Depending on that, we have to follow the same procedure. Once we do that operation, you check the balance factor is maintained. If for any of the node, if the balance factor is not satisfying, or if that node is violating the property of a balance factor, we have to apply the rotation. So this is the step. Now let us take the very simple one. Now let us try to delete the node 53 because this is a leaf node. Okay, so let me take the one which is very easy. Now delete 53 because 53 is there in the AVL tree. Now note down, after deleting we have to disconnect this link, right? So now let me draw that 14, 11, 7, 7 left child is 4 and then 8, then here 12, 12 and then 13. Fine. Now we have to delete that. After deleting, we have to calculate the balance factor. Now let us calculate quickly balance factor for all the leaf node which is 0. Now this is minus 1, 0. This is 0, 1, 2, 3, 3 minus 1. What is this? 2. Okay. Now is it right? After deleting 0, 0, 0, 0, minus 1. Now you see this 1, 2, 3 or 1, 2, 3, 3 minus 1, 2. Now this is the one which is affecting the balance factor. Now let us try to apply a suitable rotation for this. So now this is the balance factor affected. Now this is P, and then you see this is in the left. Now let us figure that this one is A. So now you see that this is violating the property, so we have to apply. See, this is the path. Okay, so once we have removed the node 53, this is the node where the balance factor getting affected, and the height of the left side of the node P is larger than the right side. So we have to rotate in the right direction. So as long as you see that it is there, that the lots of weight is at the left side. So you have to follow the case 1, because you see where that A is located. If this is P, this is A, and according to the case 1, A is in the left side of P, then this is left to left, you apply case 1. Okay, so when you apply case 1, what we have to do, A has to go to the top, this is A, and P should come to the right side of that, which is P. Okay, once this step is done, the remaining is easy. This is PR. Now let us copy 7. Okay, 7 has left side and then right side, which is 8. Okay, then 12 and then 13. Where does it go? 12 is the right side of A but less of P. Larger than A. Okay, it should come here, but lesser than P. So we can insert that subtree 12 and then 13. Fine. Now you see, now the tree is balanced. You fix this. This is A, this is P. P right child is 17. A's left subtree, we have copied all subtree to the left of A, and this is the portion left. What is that? A right subtree. Note down, A right subtree is larger than A but lesser than P. So you figure out larger than A, lesser than P. So go to the left subtree of P, then you have attach all its right subtree of A to the left of P. That's all. Procedure done. Now proceed. Now take the next node, which is delete. Now let us take the node which has 2 children. Okay. Delete 11. Now you see 11 is at the root node and that is also having 2 children. You recall that procedure in the deletion of a node which consisting of 2 children. So the procedure is that you find the in-order predecessor for that node and then you replace that node in that position and then try to modify if there is any updations in that predecessor location. Okay. Similarly, you can write or you can replace with the in-order successor, but let us do in this finding the in-order predecessor for node 11. So what is in-order predecessor for node 11? Okay, the in-order predecessor for node 11 is the largest node in the left subtree, which is 8. Fine. So we are going to replace this 8 in this position. Okay. So this node value 8 we move in this location because we want to delete 11, and then you copy the remaining subtrees as such. We have deleted that node. Now 14 and then 17. Node 18 have moved here and then node 11 is deleted. Now this is 12. Now this is 13. Okay, this is the procedure or the steps. This is the tree after deleting the node 11. Now after deleting, we have to once again calculate the balance factor. 0, 0, 0, and for this node is 1, minus 1, and for this node is 1, 2, 2 minus 1 is 1, and for this node is 1, 2, 1, 2, 3. For this node is minus 1. Now you see every node satisfies the property of a balance factor. Now this is in AVL tree. Okay. Now let us take one more deletion operation. So now again take the node which has 2 children, delete 8. Okay, in order to show the rotation as a resultant of that. So now note down, node 8 has 2 children. You know the procedure. So what is the procedure? Find the in-order predecessor for node 8, which is 7 over here. We have to replace in-order predecessor in its location. Okay, so now let me move in its location node 7 and we are going to remove node 8 and then go to its left subtree, attach 4, and then in its position what we have 14, 12, 17 and then 13. Okay, after this is the procedure. After deleting the node 8, this is the tree. Now let us check the balance factor for this. Okay, 0, 0, minus 1, 2, 1, 2, 2 minus 1, 1, 0, this 1, 1, 2, 3. Okay, find this one. Okay. 1, 2, 2 minus 1 is 1, this is 1, and now you see this is right subtree is 1, 1, 2, 3. Okay, 1 minus 3 is 2. Now as long as the balance factor violated, we fix that as P from the bottom to root, and then you see this is in this direction. Now you figure what is P and what is A. Now here also we have, this is B. Okay. After deleting this node 7, this is the step, and this node is violating the property of a balance factor. Now we figure exactly what is P, A and then B. Now you see this is right left. Okay, right left, I think this comes in the case 4. Right left, you have to apply right rotation followed by left rotation, but right rotation we have to apply here. Okay, left rotation we have to apply here. So refer case 4. Now let us proceed how to rotate step by step. Okay, first rotate here. So we have to rotate so that 12 will move up. This is 12. Note down, this is B. Once you rotate 12 in the right direction, 14 will move down. This is your A. Okay, this has gone, and then this, now 17 will come here. Now attach P. What is P? 17. So this is P. Okay, P, B, A. Fine. Now go to the left subtree of P, attach that. Right subtree of A is already attached. Now what is left? 13 is left. Where we have to attach 13 now? 13 we have to attach, which is the right subtree of B. Okay, right subtree of B, but 13 is greater than B, so we can attach 13 to the left of A. Now one more rotations we have to apply. That rotation is rotate P in the left direction. This is P. Okay, this we have to rotate and then see what is the final resultant. Now let me erase this. Okay, rotate left so that 12 will come here. Now this is B. B is in the root, and then 14. This is your A, and now 7. This is your P. Okay, and attach the remaining portion of the tree, which is 4, and then where does this goes? This goes to 17, no change, and then 13. Fine. Now after rotation, let us calculate the balance factor. Balance factor for this is 0, 0, 1, and then this is 0. Okay, so we have discussed all possible operations in AVL tree, insertion and then deletion. So you have to straight away follow the procedure for deletion in BST, same in AVL tree. While you do so, if for any node violating the property of the balance factor, you apply the rotations out of 4 cases that we have discussed. That's all. Thank you.